Welcome to Module 7, covering Analytic Geometry. In this first video, we're going to review the equation of a line. Remember that the equation of a line was covered in Math 145, and you can always look back on your D2L course shell from Math 145 for more information. Given 2 points on a line, x1, y1, and x2, y2, the slope of the line is calculated as the rise over the run, and denoted by lowercase letter m. So we use m to represent the slope. And that can be calculated as the difference in the y values divided by the difference in the x values, where x1 cannot equal x2. Remember that we can visualize this, so taking any 2 points, x1, y1, x2, y2, the slope describes the rate of change between those 2 points, and we can break it down into horizontal components as well as vertical components, where this would be a right angle. And so those two distances are the rise and the run, and we can calculate them using the difference in the respective values. So the rise would be calculated y2 minus y1, and the run calculated in the difference of the x values, x2 minus x1. So our special cases when m is equal to 0 is when we have a horizontal line, and when there's a vertical line, the slope is undefined. The first equation that we're going to look at is slope y-intercept form. We have the equation that y is equal to mx plus b, where m is your slope and b is the y-intercept. Another form of equation is the point-slope form of a line, and that equation is described by y minus y1 is equal to m times x minus x1, where m is the slope again, and x1, y1 is any point on the line. The third form of an equation to describe a line is given by ax plus by plus c is equal to 0. All three of these forms can be useful to graph a line and also determining the equation of a line to describe a problem. Depending on the information given, will dictate which form is most useful. Let's do some practice. So find the equation of a line passing through the points -3, 2 with a slope of 3, and we want to sketch the graph. We can use the given point, so we have a point with an x and y value, and we also have a slope, which is m. So we could describe this formula right away using the point-slope form of a line. But we can also work from definition of a slope. Given any point on the line and our point -3, 2 on the line, we can use a definition of the slope, which is rise over run, and plug in the given values. Now we can simplify this as y minus 2 over x plus 3. And remember that your slope is equal to 3. Now we can clear the fractions by multiplying both sides of the equation by x plus 3, and we get 3 multiplied by x plus 3 is equal to y minus 2. Now this is the slope point form. If we'd like to put this same equation into y equals mx plus b form, we can solve for y. So what I've done here is I've expanded the 3 into the brackets, and you can see you get y is equal to 3x plus 9 plus 2. Therefore, y is equal to 3x plus 11. So now if we want to determine if this equation seems reasonable, we can take a look at this y equals mx plus b form. We know that the slope is 3, and that is correct even given the question. And we also need to check that when x is equal to -3, that y is equal to 2, so that our given point actually does lie on the line. And using software like Desmos, we can confirm that these equations, in fact, graph the exact same line, and that is just represented in a different way. So to come up with a quick sketch, we know that our graph passes through the point -3, 2, which is in quadrant 2, and the slope is +3. So we'll rise 3 and run 1. So over 3, up 1. And we only need 2 points in order to graph this curve or this line, and it's going to end up crossing the y-axis at x equals 11. That's our b value for the y-intercept. This is just a rough sketch, but it gives us a good idea of what the line y equals 3x plus 11 would look like. Now we will discuss parallel and perpendicular lines. Given the equation for two lines, so line 1, L1, where y is equal to m1x plus b1, and the second line, L2, is given by y is equal to m2x plus b2, we say that the two lines are parallel, so L1 and L2 are parallel, if their slopes are the exact same. So in other words, m1 would equal m2. The slopes of L1 and L2 are perpendicular if their slopes are negative reciprocals of one another. m1 is equal to negative m2. So let's look at some examples. Find the equation of a line parallel to y is equal to 2x plus 3. So from looking at this equation, we know that the slope m is equal to 2. Therefore, the slope of the parallel line would be, and since we want any equation that is parallel to our original line, we can use y is equal to 2x. But there's actually an infinite number of possible lines that are parallel to our original equation, because we have y is equal to 2x with a y-intercept of 3. This is our original line. The line that we provided as our solution passes through 0, but you could consider any possible y-intercept. So you could add any real number to this equation, and it would also be parallel to our original line of 2x plus 3. In the next example, it says to find the equation of the line perpendicular to y is equal to 2x plus 3. So we know that the slope of this equation is 2, but the perpendicular slope, I'm going to write it as m with a little perpendicular symbol, is equal to the negative reciprocal. So it would be minus 1 over 2. Therefore, the equation of a line that is perpendicular to our original line would be y is equal to negative 1/2 x. And you could have any real number added to that equation as your y-intercept. It's really useful to use a graphing tool like Desmos to confirm your results for problems. We'll be relying on that somewhat during this course. So we had our original line, y is equal to 2x plus 3, and we wanted to determine a line that was parallel to it, which we described as y is equal to 2x. And the other thing that we did was found a perpendicular line, so y is equal to minus 1 over 2x. So we can see we have our original line here, and then we've described a parallel line and a perpendicular line. And remember that I said that you were able to describe a whole group of values, a whole bunch of lines that were all parallel by changing the y-intercept. So if I add a different y-intercept, I'm able to describe other equations that are also parallel to our original line, and you could do the same for our perpendicular line. And notice here I've added a constant with our equation, and it's described using a slider between -10 and 10, but this line always remains perpendicular to our original line, but it has a different y-intercept. The last thing we're going to look at in this review section is the distance and midpoint formulas. The distance formula is an extension of what was covered in Math 145 with right-angled triangles and the Pythagorean theorem. The distance between points P and Q, given by the coordinates x1, y1, and x2, y2, is given by the following formula. The distance from P to Q is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. The diagram we drew earlier for the slope, where we took our 2 points, so P and Q, and broke it down into the horizontal and vertical components that intersect at a right angle, we can calculate that distance, so this would be PQ, by using the Pythagorean theorem. And notice that we have our rise and our run, which is represented here, and we take the square of each of those distances and sum them and take the square root. The midpoint formula gives the point M, which is halfway between points P and Q on the line segment that connects P and Q, and the coordinates are given by x1 plus x2 divided by 2 and y1 plus y2 divided by 2. So given our points P and Q, we can find the midpoint M using this formula, which is just the average of the x values and the average of the y values. As we proceed into the next video covering conics, looking specifically at the parabola, ellipse, and hyperbola, you will need some of these formulas and concepts to complete the problems.